Welcome back, dear students, to this next lesson under scheduling algorithms, which is under process management. In the previous video, we saw how the shortest job first and the first come first serve scheduling algorithm works, and we went further to solve examples on how Gantt charts are being solved and how to analyze questions under it. We saw the advantages and disadvantages, and we concluded the video by introducing the round robin scheduling, as you can see. And what we retain is that the round robin scheduling algorithm is designed especially for time sharing system, and also it is similar to the first come first serve, but preemption is added to switch between processes. The time quantum is generally depending on the operating system. What is a time quantum? Some of you might ask, what is a time quantum? Time quantum is simply the amount of time that the operating system allocates to every process before preemption occurs. Because as it is, especially as it is used for time sharing system, the operating system provides an amount of time for each process, which after the amount of time exhausted, the CPU is being shifted or moved to another process in the ready queue. Okay, the CPU scheduler picks the first process from the ready queue, sets timer to interrupt after one time quantum, and dispatches the process in the round robin scheduling algorithm. No process is allocated the CPU for more than one time quantum in a row, meaning that if my time quantum is, for example, t, let me say t, there is no process that will be allocated with 2t in a row, except only it is the only process left in the ready queue. Otherwise, when a particular process has consumed a particular time quantum, the CPU moves to the other process. If a process CPU burst exceeds the time quantum, the process is preempted, that is, after it has consumed the time quantum, it is now preempted and it is put back in the ready queue. So just take an example like, let me say you have a row of students that you are, let me take a funny example, a row of students that you are sharing sweets and juice. And what happens is that you will tell the student that they should be in a row. The first student that comes, you give him sweets and you say, go back at the end of the line. When you come back, I will give you juice. That's why the student will each come one by one, one by one. After a student has taken his or her sweet, he will move at the end of the line. And that's what happens. So when a process consumes the burst, the time quantum, if he still needs some time for execution, he is sent at the end of the ready queue. But if it is complete, then it terminates its cycle. That's how it works. Now, let us look at an example, the Center Regional Mock 2024. It says, the following set of processes with their arrival times and burst times given in milliseconds. Draw a Gantt chart illustrating the execution of these processes using round robin in bracket quantum time equals to 4 scheduling. Determine the average turnaround time. Those are the processes. We have A, B, C, D, E. We have the arrival time. We have burst time. Arrival time is help us to know the order in which the processes arrived. So what do we have? We have the first process from 0 to 3. But you will ask yourself, why is it from 0 to 3 where the quantum time is 4? Remember that the quantum time might be above the amount of time a process needs. So A needs to run for 3 amount of units. So that's why it is from 0 to 3 and not up to 4, because he is supposed to be running in the CPU for 4 units, but he needs just 3. So he takes his unit and he leaves the CPU. He does not have long eyes. So that's how it is. So if a particular process has a burst time lower than the time quantum, then you just execute for the burst time that he needs. So from there, you realize that has complete its execution. After A, the next process was B. So we have B from 3 to 7 because the time quantum is 4. And we see that this B needs an amount of time which is more than the time quantum. So he will first of all consume the time quantum which is 4. And since he started at 3, that's why we have from 3 to 4. That makes that B is now left with 2 units because he has already consumed 4. So he's left now with 2 units. We move now to C. 4 units also, as the time quantum says, so from 7 to 11. And since C needs 4 units just like the time quantum, it shows that C has also completed its execution. D needs 5, but the CPU gives him 4 first of all. So take your 4 from 11 to 15, meaning that what we are left with 1 unit. E needs only 2, but the CPU gives him 4, so he will just take his 2. There is no processor who has long eyes. No, you only execute for the amount of time you have. So E will execute from 15 to 17, as you can see, and you see that E has complete its execution. So you see that the processor provided a time quantum for each of the processes in the order in which they are high, that is for A, B, C, and D. For the processes whose burst time are less than the time quantum, they complete the execution, which in the case which is less than or equals to the time quantum, they have completed their execution, just like A, C, and E. But for those whose burst time are above the time quantum, they will need to be executed again for the amount of time left. So we start back, A complete, so we now come to B, but this time around B needs only 2 units and not more 6, because it has only consumed 4, so he needs only 2. So B will be executing from 17 to 19, and that's how he completes its own execution. C is complete. We come to D. D needs only 1, so that's why we have 20. So D also complete its execution. If it's that D here was, for example, 9, 9 minus 4 will give us 5. Then D will consume 5 again before we come back and we consume the remaining 1. So we verify if everything is okay. 8 plus 6, 9, plus 4, 13, plus 5, 18, plus 2, 20, which is the same thing as the difference between the last value and the first value. So our Gantt chart is okay. So that is the table. The arrival time and burst time as given. Completion time, A finishes at 3, B finishes at 19. Yes. So when you see that B has 2 instances here, you take the last instance. So B completes at 19, C completes at 11, D at 20, not 15, there's an error. D completes at 15, at 20, sorry, D completes at 20. Then E complete at 17. So there's an error with this one here. Take note, dear students. Then around time is completion minus arrival. 3, 17, 7. Here is supposed to be 20. 20 minus 6, so you're supposed to have 14. And here we have 9. So that's what we have turnaround time. So this particular value has an error. So I'm expecting you guys to comment in the to put the right turnaround time as a comment to this video, dear students. So I hope when it comes to round robin, drawing the Gantt chart is not a problem. Whatever the case, we still have 2 sections, that is the exercises after the differential algorithms, and the end of chapter where we are going to solve past GC and regional mock questions. For those of you who might still have problem in round robin, I will advise you to comment, or you reach till the end of the chapter where we shall be solving those questions, and you might see there might be an explanation that will make you to understand better. Okay, these are some notes that you need to take note under round robin. If there are n processes in the ready queue with the time slice, take note that time slice and time quantum are the same. With time slice cure, then each process gets 1 on n of the CPU time in chunks of at most cure time units. Meaning that if I have 5 processes, then each process take 1/5 of the CPU time in chunks of at most cure time units. When you say at most, it means that what? It can be less than that, but it can never exceed. It can be less, sorry, it can be less than or equals to cure, but it can never exceed cure. That's why we say 1 of n CPU time in chunks, that is in blocks, as you can see, chunks of at most cure units. Each process must wait at most n minus 1 times cure units. Very important. So if there are 5 processes and the time slice is 4, as we have here, then each process will have to wait at most 4 times 4, which is 16 time units, until its next time slice. Very important when it comes to MCQ. The performance of the round robin algorithm depends heavily on the size of the time quantum, which is very important. If the time quantum is very large, the round robin policy is the same as the first come, first serve. I think this question came in the Northwest Regional Mock 2022 or 21. Yes, this question was being asked that when the time quantum of a round robin is very large, it is similar to, and the answer there was that it is similar to a first come, first serve. If the time quantum is very small, the round robin approach is called processor sharing and appears to the user as though each of the n processes has its own processor running at 1 on n the speed of the real processor. But this is just in theory. So take note of the instances where the time quantum is large and when it is small. We move to the next scheduling algorithm, which is the shortest remaining time first, SRTF. This is the preemptive counterpart of shortest job first and useful in time sharing environment. So just like the round robin, the shortest remaining time first, also known as the shortest remaining job next, is useful in time sharing environment. In contrast to shortest job first, which executes a process till the end despite the entry of a process with a smaller burst time in the ready queue. In SRTF, when a new process joins the ready queue, short-term scheduler compare the remaining time of the executing process and the new process. If the new process has the least CPU burst time, the scheduler selects that job and connect to the CPU. Otherwise, continue the whole process. So what happens here is that we know that shortest job first is non-preemptive. That is when we start with a particular process with complete execution, no matter the size of the other processes. When I talk of size, I'm talking about the burst time. In shortest remaining time first, when a process is being executed, if another process enters the ready queue with a burst time lower than the amount of time left for the currently executing process to terminate, then the scheduler will swap those two processes and concentrate, that is, and start by executing the process with a smaller burst time. So what do we have here? To easily draw the Gantt chart for a shortest remaining time first, dear student, because this is one of the scheduling algorithm that students faces a lot of problem when drawing it because it's a little bit tricky. But due to the fact that you are present in the Byte family, such tips are always given to you no matter the chapter. So when it comes to shortest remaining time first, to easily draw it, the first step is to draw the Gantt chart with the spaces sectioned according to arrival time. So first of all, draw an empty Gantt chart and you section it according to the arrival time. Fill the spaces with the process according to arrival time and according to burst time in case you have more than one process already. Very important, this second point. The third point now, next, fill the remaining processes following the shortest job first scheduling. Very important, very easy. Let us look at what we are saying. Draw a Gantt chart illustrating the execution of the processes using shortest remaining time first scheduling. So we're talking about this same diagram, center regional milestone for the extract. We're talking about it. So I eliminate this for you guys to see. So the first step is asking us to draw the Gantt chart with the spaces section, as you can see. So this is what I have. So I first of all draw my empty Gantt chart with the different scheduling, the different arrival time, as you can see, 0, 2, 4, 6, 8. That is what we have. Now, at time 0, only A is present because A is the only process arriving at time 0. So he will run till the next arrival. Meaning what? I first of all run A from 0 to 2. Meaning that A is now left with 1 unit because from here, it means that he has consumed 2 units. So he's now left with 1. At time 2 now, that is where B enters the CPU. What happens? At time 2, A and B are present and A has the smallest burst time because when there are only two processes, we now compare who is having the smallest burst time and we execute it. And we are seeing that A has the smallest burst time because A is left with 1 unit, whereas B has 6 units. So we will run A, but look at, in this case, it is 2 units. So I'm going to run A for 1 unit and B for the rest of the unit till the next arrival. That is what we are going to have. So that is what I'm going to have. So I will run A for 1 unit, that is from 2 to 3. Then I run B till the next arrival, meaning that A is complete and B has consumed 1 unit. So it's now left with 5 units. At time 4, only B and C are present because A has already completed his execution. So at time 4, B and C are present. And C has the smallest burst time because B has 5 while C has 4. So I'm going to execute C till the next arrival. So as you can see, this is the C here and he has consumed 2 units. So C is now left with 2 units, as you can see. Now, at time 6, B, C, and D are present because D enters at time 6. And when you compare, B has 5, C has 2, and D has 5. So C has the smallest burst time. So we will run C till the next arrival. That's why you have C here from 6 to 8, meaning that C has completed its execution, as you can see. Now, at time 8 now, at time 8, B D and E are present. And remember what we said here. We fill the remaining process following the shortest job first scheduling. So at time 8, B, D, and E are present. That is B, D, and E are present. Who has the smallest best time? It is E. So we will execute E till it completes its execution because we don't have any other arrival time again. And we said that if there is no more arrival time, we now take a process and we execute till the end. So I'm going to execute E from 8 to how many? To 10. Correct. That is what we are going to have. And E is complete. Now, I am left I am left now with B and D. B has 5, D has 5. Since both have the same burst time, we follow the first come, first serve. Yes, because we saw on shortest job first that if we have two processes having the same burst time, we execute them in the first come, first serve. And since B came before D, so I'm going to execute B first. So I will execute B from 10 to 15. Then D from 15 to 20. So this is the Gantt chart as you can see. Another student could simply say from A from 0 to 3, B from 3 to 4, C from 4 to 8, E from 8 to 10, B and so on. So this particular Gantt chart is similar to this one. They are the same as you can see there today. So I just use this for you guys to clearly see how to easily draw the Gantt chart when it comes to shortest remaining time first. As you can see, this is our turnaround time. So I will expect you guys to calculate. So the average turnaround time is 7.2 units. Now, let us look at another example because I know that this particular algorithm is somehow tedious for some students. So let us look at another example. The Southwest Regional Mock March 2022 question 3 sub 3. It says 4 processes P1, P2, P3, and P4 are scheduled to use a single CPU. The following table shows the arrival time and duration of each of the 4 processes. If the system uses a preemptive shortest job first scheduling algorithm, because take note, shortest remaining time first is the same thing as preemptive shortest job first algorithm. Draw a Gantt chart to show how these processes will be scheduled. Determine the average waiting time and average turnaround time for these processes. That's a 6 marks question. We do the same thing. We draw our Gantt chart according to our time. That is what we have. So 0, 2, 4, 5. That is what we have. First thing, at time 0, only P1 is present, so he will run to the next arrival. So I have P1 to be running from 0 to 2, meaning that he has already consumed 2 units and he is left with 5. At time 2, P1 and P2 are present. And when you compare, P1 has 5 units, P2 4 units. So you see that P2 has the smallest burst time, which is 4. So we will run P2 till the next arrival. That's why you have P2 at this level from 2 to 4, meaning that he has also consumed 2 units and he is left with 2. Next, at time 4, that is when P3 enters. So I have P1, P2, and P3 present. P1 left with 5, P2 left with 2, P3 1 unit only. And you see that P3 has the smallest best time, so we will run P1 to the next arrival. Unfortunately, the next arrival is only after 1 unit of time. So that is why you have P3 here from 4 to 5. In case here was 6, then it means that it is from, in case this was from 4 to 6, you see that it is 2 units, whereas P3 needs only 1. It means that, as in the first example, I'm going to run P3 from 4 to 5, then the other 1 unit that will be left will be allocated to P2 because at time 4, there are 3 of them, P1, P2, P3. And since P3 will be completed, I'll be left only with P1 and P2, and the one having the smallest is P2. So in that case, I will have executed P3 from 4 to 5, then P2 from 5 to 6, but that's not the case. Now, at time 5, so P3 is okay. At time 5, I have P1, P2, and P4 are present. 5 units, 2 units, 4 units. You see that P2 has the smallest best time. So I will execute P2 till it completes. Why till it completes? Because there is no more arrival time. So I'm going to execute P2 from 5 to how many? To 7. That is how P2 is done. And now I'm just executing them now following the shortest job first, where P4 will be the next before P1. So now you are left with P1 and P4. P4 has the smallest best time, so you run P4 till it complete, then P1. So I have P4. P4 needs 4 units, so from 7 to 11. Then P1 from 11 to 16, as you can see. Let us compare. 7 plus 4, 11, plus 1, 12, plus 4, 16, which is the same thing as the difference between the last and the first. So our Gantt chart is okay. So guys, I will give you as work to calculate the turnaround time and the waiting time, and you compare with the answers that we have here. So you see that this is P1 from 0 to 2, P2 from 2 to 4, P3 from 4 to 5, P2 again from 5 to 7, and so on and so forth. And I will always and I will also encourage you, dear students, to always make sure that the size allocated for a particular process should be proportional to the size. As you can see that P3 is only 1 unit, it is smaller than this and this. P4 and P1 are larger. The time there is 4 units, there is 5 units, so they are larger as compared to this one. It is very important because it enables you to like easily identify certain errors, and for the marker also to not like make some kind of errors when marking. So when drawing a Gantt chart, always make sure that the size of a particular process is proportional to the burst time that it is consuming at that particular instant. So the turnaround time is 7 seconds and the waiting time is 3 seconds. And it is because here in the table they said the duration is given in seconds. Okay, guys, we reached the end of the video. That is already four different scheduling algorithms that we saw. In the next video, we shall look at the last scheduling algorithm. If you know which algorithm we are talking about, I will advise you to put it in the comment section. In our next video, we shall look at this last scheduling algorithm, which can be both preemptive and non-preemptive, and we shall conclude with some exercises and the difference between preemptive and non-preemptive scheduling algorithms before we enter inside another aspect of process management, which is nothing other than deadlock. Do not forget to like, to subscribe, and to share for our community to grow, dear students, and see you in the next video.